Consider a sample of crystal, and when a beam of X-rays is incident on it, this will get diffracted in all directions from each lattice points. And I have considered a detector here in that direction. If the diffracted rays in that specific direction contributes to the constructive interference. So I am getting a constructive interference in this direction. According to Bragg, he considered this diffracted rays which contributes to the constructive interference actually resembles the reflection from a set of parallel atomic planes. Okay, this is the angle of reflection, and that is equal to angle of incidence. So the diffracted rays which contributes to the constructive interference resembles the reflection from set of parallel atomic planes that Bragg considered. And if I move this detector in another direction, I may get a destructive interference in this direction. And if I move again this detector in another direction, if I am getting a constructive interference in that direction, according to Bragg, this diffracted rays which contributes to the constructive interference resembles the reflection from another set of parallel planes. Angle of reflection is equal to angle of incidence. Okay, so by considering this parallel atomic planes, we can study all the internal characteristics of this crystal. Okay, so and Bragg derived an equation. We all are familiar with that equation. N lambda equal to 2d sin theta. That is the path difference. Path difference is equal to the integral multiple of the wavelength lambda. Okay, we all are familiar with this equation. We all studied in our graduate level this equation. So I am not doing the derivation here. This is the equation N lambda equal to 2d sin theta. This is Bragg's equation, Bragg's law, which is the consequence of periodicity of this lattice. Okay, so the importance of this Bragg's law is by considering different set of parallel planes, we can study all the internal characteristics of a piece of crystal. Okay. Any non-sinusoidal periodic function can be expressed by a sum of sinusoidal periodic functions like sines, cosines, or complex exponentials. And any local physical properties invariant under translation, such as charge density, electron number density, or magnetic moment density. Okay, under translation, it's local physical properties invariant under translation T. Let me consider a two-dimensional lattice. Okay, and this is a translation vector which connects 2 points having similar surroundings. Any local physical properties invariant under this translation means, for instance, the number density at this point is equal to number density at this point. The charge density at this point is equal to charge density at this point. Let me consider an origin here. This is O, and this is the position vector of this point, and this is the position vector. R plus T is the position vector of this point. The number density at this point is equal to the number density at this point. That means N of R is equal to N of R plus T. Okay. Such periodicity creates an ideal situation for Fourier analysis. Let me consider a one-dimensional lattice. This is a one-dimensional lattice, and this is the point X, and this is the point X plus A. This lattice has a period A, so this is X plus 2A. In that one dimension, the number density at the position X is a non-sinusoidal periodic function, can be expressed by the sum of sines and cosines. Okay, so n of x equal to n naught plus sum over p greater than 0, cp cos 2 pi px over a plus sp sin 2 pi px over a. Okay, where cp and sp are real constants, are known as coefficients of Fourier expansion. P's are positive integers, p greater than 0, p's are positive integers, and the factor 2 pi over a, the factor 2 pi over a ensures that this has a period a. Okay, this term ensures that this has a period a. Let us check how. Let us consider the number density at the position x plus a. Okay, n of x plus a equal to, we need to substitute x plus a for x. That is equal to n naught plus sum over p greater than 0, cp cos 2 pi p over a. We need to substitute x plus a for x. So 2 pi p over a, x plus a, plus sp sine 2 pi p, x plus a over a. Okay. And we can expand this. That is equal to n naught plus sum over p greater than 0, cp cos 2 pi px over a, 2 pi px over a, plus 2 pi p a over a. A and a will get cancelled and we will get 2 pi p plus 2 pi p. And plus sp sine 2 pi px over a plus 2 pi p a over a. A and a will get cancelled. And that is equal to, we know cos theta plus 2n pi, where n is an integer. If n is an integer, cos theta plus 2n pi equal to cos theta, as well as sin theta plus 2n pi equal to sin theta if n is an integer. Okay, here we told p is a positive integer. P's are positive integers. So 2n pi cos theta plus 2 p pi equal to cos theta. Okay, that means cp cos 2 pi px over a, and sin theta plus 2 p pi equal to sin theta itself, sin 2 pi px over a, and that is equal to n of x. Okay, that is equal to n of x. We will get the same terms in this equation. That is equal to n of x. And in a compact form, the equation 2 can be written as the number density n of x equal to sum over p np e raised to I 2 pi px over a. And we know number density is a real function. And here in the RHS, right hand side of this equation, e raised to I 2 pi px over a is a complex function. Okay, and we need to make sure that RHS is also should be a real function, real part. Okay, so and here the p can have positive, negative and 0 values. Okay, and p's are integers. P can have positive, negative and 0 values. To make sure that RHS of this equation is real, we need to apply a condition np equal to n minus p star. N minus p star is the complex conjugate of n minus p. Okay, and let phi equal to 2 pi px over a, and n of x equal to this is equation 5. N of x equal to sum over p np e raised to I phi. Okay, np e raised to I phi. And I can expand this term. N of x equal to sum over p np e raised to I 2 pi p x over a, like etc. plus the p starting from minus infinity. So etc. plus, I am considering just 3 terms n minus 1. When p equal to minus 1, n minus 1 e raised to I 2 pi px over a is cos p is minus 1. So 2 pi x over a, cos minus theta equal to cos theta, minus I sin 2 pi x over a. Okay, sin minus theta equal to minus sin theta, plus n naught plus when I apply 1 for p, n1 cos 2 pi x over a plus I sin 2 pi x over a plus etc. Okay, I can expand this term in this way. And here in this step I am considering all the symmetric terms of right side of n naught and left side of n naught generally. Okay, right side of n naught, when I am adding all symmetric terms in the right side and left side, I can write in a general form. The right side of this equation is np cos phi plus I sin phi, plus left side of this equation is n minus p cos phi minus I sin phi. Okay, then I am adding these two symmetric terms, not two symmetric terms, this symmetric terms. np cos phi plus I sin phi plus n minus p cos phi minus I sin phi, and that is equal to np plus n minus p cos phi plus I np minus n minus p sin phi. Okay, and that is equal to, we have applied a condition np equal to n minus p star, and that is we need to substitute this value here, n minus p star plus n minus p cos phi plus I n minus p star minus n minus p sin phi. Okay, and that is equal to 2 into real part of np cos phi plus 2 into imaginary part of np sin phi. I'll explain it. Let me consider n minus p equal to a complex number a plus ib. Okay, complex number a plus ib, and n minus p star is equal to complex conjugate a minus ib. When I am adding n minus p plus n minus p star plus n minus p, I will get n minus p star plus n minus p, I will get 2a. This plus this one will provide the value 2a. That means 2 into real part of n minus p star. Okay, this is the real part of n minus p star. 2 into real part of n minus p star. N minus p star is equal to np. So 2 into real part of np into cos phi plus 2 into imaginary part of np sin phi. Okay, and if I subtract n minus p minus n minus p minus n minus p will provide minus 2ib. Okay, minus 2ib, and if I multiply this with this I will get plus 2ib plus 2ib plus 2 sorry okay plus 2i. If I multiply minus 2ib with this I'll get this as plus 2b. Okay, minus I and plus I will get plus, if I multiply minus I with plus I'll get plus 1. So I'll get 2b. 2b means 2 into imaginary part of n minus p star. Imaginary part of b is imaginary part of n minus p star. Imaginary part of n minus p star is equal to np. That means 2 into imaginary part of np sin phi. Okay. And I had a mistake. This is cos phi minus 2 imaginary part of np sin phi. Okay. In three dimension, the number density can be written as n of r equal to sum over g ng e raised to I 2 pi g dot r. Okay. This is in one dimension, and in two dimension, number density n of r at the position r equal to sum over g ng e raised to I 2 pi g dot r. Okay, the vector g we need to define such that the number density is invariant under translation. Okay, we will do that later. And next, the inversion of Fourier series. Here n of x equal to sum over p np e raised to I 2 pi px over a. I need to define np, and I am defining here np equal to a inverse integral 0 to a dx n of x e raised to minus I 2 pi px over a. Let me put it as equation 7. Okay. Substitute equation 3 in equation 7. Equation 3 is this one, number density n of x equal to sum over p np e raised to I 2 pi px over a. Okay, this value I need to substitute in this equation. So I'll get np equal to a inverse n of x I need to substitute in this equation. np equal to a inverse integral 0 to a dx sum over p dash np dash e raised to I 2 pi p dash x over a for nx e raised to I 2 pi px over a. Okay, I am using here p dash, term p dash, since if I expand this one, n of x, I need to expand from minus infinity to plus infinity. So p's are positive, negative or zero values. P's can have positive, negative or zero values. Okay, it's a series. So here I am using that series. Here I am finding NP. Okay, a specific term NP, and that P is using here NP, that P is using here. If I am finding N1, that N1 equal to A inverse integral 0 to A dx n of x e raised to I 2 pi 1 x over A. But still there, n of x is there. N of x is defining from minus infinity to p's. In that n of x, the p's can have values from minus infinity to plus infinity. So this p and the p included in n of x may be same or different. That's why I am using p dash here. That is np equal to A inverse 0 to A dx sum over p dash np dash e raised to I 2 pi p dash x over A e raised to minus I 2 pi p x over A. Okay, and later we will consider two different cases that when p dash equal to p and when p dash not equal to p. Okay, so this is equal to A inverse. I am taking the sum outside. Sum of p dash np dash integral 0 to A dx e raised to I 2 pi p dash minus p into x over A. Okay, and this is equation 8. So I can expand this in this way. This is sum over p dash np dash integral dx e raised to I 2 pi p dash minus p x over A. Okay, this is a series from minus infinity to plus infinity. So I can expand in this way, and that is equal to A inverse etc. plus. Okay, I am writing only few terms in that series. Plus, if p dash is equal to minus 1, that is n minus 1 integral 0 to A dx e raised to I 2 pi minus 1 minus p x over A plus n naught integral 0 to A dx e raised to I 2 pi minus p x over A plus etc. Okay, and in this series there are two kinds of terms. In one term p dash will be equal to p. Okay, p dash and p are integers. So in one term p dash is equal to p. Okay, for instance, if p is minus 1, then this term is p dash equal to p. Okay, all remaining terms are p dash is not equal to p. Okay, so generally we can verify what will happen if p dash is not equal to p. The terms with p dash is not equal to p, and the terms with what will happen to the terms with p dash is not equal to p and p dash is equal to p. There is only one term having p dash is equal to p. Okay, and what will happen to the remaining terms in this series? So integral 0 to, we can find out the general form. We can take the general form integral 0 to A dx e raised to I 2 pi p dash minus p x over A equal to, we can integrate it in, and we will get e raised to I 2 pi p dash minus p x over A is integrating, and the limit is from 0 to A, and that is equal to A over I 2 pi p dash minus p e raised to I 2 pi p dash minus p minus 1. Okay, if we apply the upper limit, we will get this term, and the lower limit we will get that is equal to 1. Okay, and that is equal to 0 because p dash is an integer, p is also an integer. When we subtracting this integer from another integer, we will get another integer. Okay, so if that integer is n, then cos 2 pi n plus this term is cos 2 pi n plus I sin 2 pi n, and sin 2 pi n is equal to 0 and cos 2 pi n is equal to 1 if n is an integer. Okay, so this term will be equal to 1 when p dash is not equal to p. P dash is not equal to p. This term will be 1 and 1 minus 1 equal to 0. Okay, that means the terms, all the terms except 1 having the value p dash equal to p will be equal to 0. Okay, and the term is remaining is which p dash equal to p, that is np equal to A inverse np. Okay, A inverse, only the term remaining is P dash is equal to P, that is np integral 0 to A dx, integral 0 to A dx, and here P dash is equal to P, so P dash minus P equal to 0, so that means e raised to 0 is 1, integral 0 to A dx, and that is equal to A inverse np. If we integrate this one, we will get x from limit is from 0 to A, and that is equal to A inverse np into A inverse np into A inverse is 1 by A, np into A, we will get this A and A inverse will get cancelled, and that is equal to np. Okay, actually what we have proved here, we have defined np in this way, and we substitute the value of nx here. We got that np is equal to np. That means this is the equation, compact equation for number density at the position x, and that is equal to sum over p np e raised to I 2 pi px over a, and this tells us we can define the constant np, we can define the term np as A inverse integral 0 to A dx n of x e raised to I 2 pi px over a. Okay,